I want to prove that the integral from 0 all the way up to positive infinity of e to the power of negative x squared dx is equal to half of square root of pi. So this integral is also known as probability integral or Euler-Poisson integral. So to prove this, we'll first prove this inequality and prove this limit. This Wallis formula. So first of all, here is my claim. E to the power of t is always greater than or equal to 1 plus t. There's no restriction to the real number t. So here's why. So construct the function in terms of t. E to the power of t minus 1 minus t. So what is the derivative of t? E to the power of t minus 1. Right? So when t is positive, my derivative is obviously positive. And also when t is negative, right, e to the power of negative, obviously negative. Of course, when t is equal to 0, right, my derivative, of course, is 0. Right, so that means my function f of t is actually increasing from 0 all the way up to positive infinity. And from negative infinity to 0, my function should be decreasing. So not only my function reaches local minimum at point 0, but it's also a global minimum, right? So meaning my functional value, f of, what is f of 0? F of 0 is t e to 0 minus 1, 1 minus 1 minus 0, 0. Right? So my functional value can be no less than 0. 0 is my minimum value, right? F of t is greater than or equal to 0. Greater than or equal to 0, right? Meaning e to the power of t plus 1 plus t onto the other side, right? Greater than 1 plus t. This is really true. No restriction to t. Now if I let t equal to x squared, then I have e to the power of x squared larger than or equal to 1 plus x squared. Right? If I take the reciprocal on both sides, right, that's 1 over e to the power of x squared, which is just e to the power of negative x squared. Change the direction, right? The reciprocal of this is 1 over 1 plus x squared. That is the right-hand side of the inequality, right? So now, if I let t equal minus x squared, right, then I easily have the inequality e to the power of minus x squared larger than or equal to 1 minus x squared. That is my left-hand side inequality. Now, in this Wallis formula, the limit of this sequence is equal to half pi. This is well known. But in reality, in practice, we use the following limit more often. Right? This is more useful, more practical. The reason is only because since the limit of this sequence is equal to half pi, what if we square root both sides? Right? So in other words, if we take the square root, so we have the limit of square root of, what was that? 2n double factorial on the top. And 2n double factorial meaning the product of all the even numbers starting from 2 all the way up to 2n And if we square root the bottom, what do we have? First of all, 2n plus 1 double factorial means the product of all the odd numbers starting from 1 all the way up to 2n plus 1. So therefore, 2n plus 1 double factorial can be break into 2n plus 1 times 2n minus 1 double factorial, right? And we have another 2n minus 1 double factorial, right? That's 2n minus 1 double factorial squared. After we take the square, we only have 2n minus 1 double factorial, right? Remember, we broke 2n plus 1 double factorial into two parts. First part was 2n plus 1, right? 2n plus 1 takes its square root, right? And take the square root. That is the square root of pi over 2, right? The limit of this. Now, if we divide this over, limit, divide it over. All right, first of all, let me just copy down the 2n double factorial over 2n minus 1 double factorial, right? And I still have this. Right? Still have square root of 2n plus 1 at the bottom. Because I consider this as a whole entity, put it on the top. And after I divide this over, right, this will sit on the bottom as well. Right, sit at the bottom. Right, the fraction line, right, sitting at the bottom. So this limit is equal to 1. Right? So we can, every time we see this sequence at the top, we can always replace it with the bottom when we calculate limits. If it's under multiplication or division, right? If it's subtraction or addition may not be true, but if it's multiplication or division, we can substitute this with that, right? Always safe. Now I'm going to restrict x in between 0 and 1. Under this restriction, 1 minus x squared is non-negative. Therefore, the middle part is always positive. So is the right-hand side, right? If we raise to the power of some positive integer on every side, inequality still remains true. Right, 1 minus x squared to the power of n, some positive integer. So less than or equal to e to the power of minus n x squared. Less than or equal to 1 over 1 plus x squared. Quantity to the power of n. Now, if we just, under this restriction, integrate on every side, right? Integrate from 0 to 1. 1 minus x squared to the power of n dx. Less than or equal to integrate from 0 to 1. E to the power of minus n x squared dx. Less than or equal to integral from 0 to 1. 1 over 1 plus x squared. Quantity to the n dx. Right. So this integral denoted as I1. This integral denoted as I2. This integral denoted I3. Now for I1, I just let x equal to sine theta. Right, then dx is equal to cosine theta d theta. Right? Also change the boundaries. I1 is equal to when x is equal to 0, theta is equal to 0. Right, when x is equal to 1, theta is equal to half pi. Right. Integrand becomes 1 minus sine square, that's cosine square, raised to the power of n, right, cosine to the 2n dx times cosine theta dx, d theta, cosine to the power of 2n plus 1. Of theta, d theta. All right, so this time, what is, okay, the well-known formula, right? This, I think, is called Wallis integral, right? So cosine raised to the power of some positive integer from 0 to half pi is simply equal to, on the bottom we have the power, the double factorial, 2n plus 1. The top, just reduce it by 1, 2n, then double factorial. And since it's odd power, therefore we don't have to multiply by half pi, just leave it. Okay, so what's I2? I2, we simply let t equal to square root of n times x. Right, that way, dx is simply just 1 over square root of n dt, right? This is a constant, 1 over square root of n. So also change the boundaries, right? So therefore, I2 is equal to, when x is equal to 0, t is equal to 0. When x is equal to 1, t is equal to square root of n, right? Then t e to the power of square both sides, n x squared equal t squared, right? Minus t squared dt, dx dt, right? Constant multiply out, right? Equal to 1 over square root of n times this. And this is my I2. Now what is I3? Right, I3. I let x equal to tangent theta, right? Every time we see 1 plus x squared, that's our usual substitution. So dx secant square d theta. Also change the boundaries. Right, when x equal to 0, theta equal to 0. When x equal to 1, theta equal to pi over 4. Right, so on the bottom we have 1 plus tangent square. Right, that's secant square. Secant square to the power of n, secant to the 2n, secant to the 2n of theta dx. Dx is secant square theta d theta. Right. So therefore, I3 is equal to 0 to pi over 4. Again, secant square distribute to the bottom. Bottom we have secant to the power of 2n minus 2. Right? But because overall it's a reciprocal of secant, so therefore simply just cosine to the power of 2n minus 2 of theta d theta. Right? Also, because cosine over the interval from 0 to half pi is always non-negative. Therefore, if I stretch this interval all the way up to half pi, this whole integral should be bigger, right? So less than or equal to 0 all the way up to half pi, right? The same integrand. Now, again, using the well-known formula, right? Copy down the power, 2n minus 2, then double factorial. Power reduced by 1, right? 2n minus 3, then double factorial. Since the power is even, therefore multiply by half pi. Now I've worked out the value of the first integral, I1. Worked out this integral, right, to be this value. And I've loosened the integral to be this value, right? So in other words, let me just rewrite into just, again, this inequality. I1 is less than or equal to 2n double factorial over 2n plus 1. Double factorial is less than or equal to the 1 over square root of n, from 0 to square root of n, e to the minus t squared dt, less than or equal to 2n minus 3 double factorial 2n minus 2 double factorial times half pi, right? If I multiply every side by square root of n, then what do I have? Right, square root of n and square root of n. Right. And later, now we're going to let n approach infinity. Right? Let's look at the left-hand side. Left-hand side. The limit of left-hand side. Is there a limit? Now remember, I've proven that the limit of this sequence over that sequence is just 1, right? Every time we see the top, we can replace it with the bottom, as long as it's under multiplication, right? So do we actually have the top sequence here? 2n double factorial, 2n minus 1 double factorial. Not exactly, but again, we can rewrite the bottom into just two parts, right? 2n plus 1 times 2n minus 1 double factorial. Right? So therefore, we can perhaps apply our theorem. Copy down square root of n, right, over 2n plus 1, right? 2n double factorial, 2n minus 1 double factorial, right? This latter part can be replaced with the bottom, right? Equal to limit of just square root of n over 2n plus 1 times square root of 2n plus 1 times square root of pi over 2. All right. Equivalence substitution. Now, square root of 2n plus 1 and 2n plus 1, they can just simplify down to copy down square root of n, right? They simplify down to square root of 2n plus 1 at the bottom times square root of pi over 2, right? So this part, square root of n, right, over square root of 2n plus 1, divide top and bottom by square root of n, right? Simply we have approaching 1 over square root of 2. Yes. So this part approach, it's easily verifiable, right? Approaching 1 over square root of 2. So that the whole thing approaches square root of 2, right? They just become 2 at the bottom, square root of pi at the top. So now I've successfully figured out the limit of the left-hand side. That is half of square root of pi, right? Now the right-hand side limit. Is there a limit? I believe so. Right-hand side. again, can we use equivalence substitution? Right. Right. 2n. What's the pattern here? Right. Top sequence, right? Double factorial. We have even number, right? Also, this double factorial, odd number, right? This even number is always 1 unit larger than the bottom even number, or bottom odd number. What's the pattern on the bottom, right? Inside the square root here, right? What's the pattern here? This odd number is exactly 1 unit larger than this even number, right? So can we find out this pattern? So in here, what do we have here? 2n, that's an even number factorial, right? Even number factorial. Exactly 1 unit larger than this odd number, right? Odd number factorial. Except that's the reciprocal of that, right? Reciprocal. Therefore, we have to, when we substitute it, we have to substitute its reciprocal. Right? Also, we don't substitute by this one. Instead, we will substitute. We're gonna increase the even number by 1, right? Increase 2n minus 2 by 1 becomes 2n minus 1. So in the end, we can substitute by, let me just copy down the pi over 2, copy down square root of n, and then we can substitute. Substitute, like I said, this square root inside here we have 2n minus 1, right? Okay, reciprocal, right? 1 over square root of 2n minus 1. Right, square root of pi over 2, right? Because here we happens to be the reciprocal. Therefore, the reciprocal of this is just 1 over, except we have to change the inside 2n plus 1 into 2n minus 1, because the pattern is that this odd number is 1 unit larger than this even number, right? 1 unit larger than this even number. Right? So, pi over 2, square root of pi over 2. Right? They just can simplify down to just, first of all, square root of pi over 2, right, at the top. Then we have the following, square root of n over square root of 2n minus 1, right? Same reason, divide top and bottom by square root of n. I believe in the end we have on the top, on the bottom, we have square root of 2n over 2, square root of 2, 1 over. I believe this can be easily verified, approaching 1 over square root of 2, right? So therefore, square root of 2, square root of 2. 2 at the bottom, right? Square root of pi, right? That's the limit of my right-hand side. Okay. Really approaching half of square root of pi, right? I've also shown that the left-hand side limit is the same thing, right? So the middle, also the same limit, half of square root of pi, because as n approaches infinity, square root of n also approaches positive infinity, and therefore we have half of square root of pi.